which is electrolytic processes. The first section we'll be going over is what physical mechanisms make our remediation method function. On the right side, we have a picture of an example of a setup of an electrolytic process taking place so you can have a visual of it. Basically, what happens in our process is that an outside DC power source is connected to an anode and a cathode that each sit inside of a well that sit opposite each other. An electrolytic solution is then injected into the wells. We'll talk more about how the solution exactly works later. When the electrodes generate direct current, it makes the ions in the soil move around, and the ions will cooperate in such a way that removes the desired contaminants, which are usually heavy metals and/or organic compounds. The first main mechanism of electrolytic processes is ionic migration, is the movement of the ions in the soil that begins when the electrodes are placed and turned on. The ions movement makes a diffuse double layer. The layer is essentially just how the ions are brought closer and further towards the electrode depending on the electrode's charge. The diffuse double layer holds the contaminants and the original soil components inside itself, and it increases the contaminant ions drift as they navigate the soil and as more current comes in from the electrodes. This process is called electroosmosis. We'll talk more about it later on in the presentation. Both average charge density and hydration products will cause the diffuse layer size to be either larger or smaller. We have another picture off to the right that illustrates ionic migration visually if you want to pause and take a look. The second main driving mechanism behind electrolytic processes is called electrophoresis. Electrophoresis is essentially just how charged particles move relative to the fluid they are in while an electric field is present. It happens at the same time as ionic migration does, but it occurs in the opposite direction of the migrating ions. Electrophoresis-driven ions move from the cathode to the anode, and the solution that facilitates the ions' movement will flow from the positively charged area to the negatively charged area instead. Also, despite electroosmosis also occurring during ionic migration, mainly is driven by electrophoresis. The graphic on the right shows the forces acting on the ions during electrophoresis. Again, feel free to pause the video if you want to look at the graphic more. The two main mechanisms I discussed come together to make the electrolytic process work. Electrophoresis in a way dictates where the ions move the most, and it drives the most electroosmosis flow. Ionic migration dictates less than electrophoresis, but it removes the most contaminant ions since it makes them migrate. Electroosmosis also lowers the soil's pH, and a low pH is quite helpful as it prevents metal from attaching to soil particles. Now we're moving on to some extra information on electroosmosis. At its most basic level, electroosmosis is when a solution flows on a surface while being affected by an electric field. It makes both a diffuse double layer and a rigid/fixed layer inside of the electrolytic solution. As mentioned previously, electroosmosis is mainly a part of the electrophoresis process. The cartoon on the right shows how ions move during electroosmosis, and you can pause to look at it more if you would like to. Now let's get into some of the ways the contaminants are actually removed in electrolytic processes. There are several different methods for removal, and I'm going to list a few of them. Firstly, there is precipitation, where the contaminants exit the soil as precipitation on one of the electrodes. Complexing is next, where ion exchange resins are used to separate the contaminants out of the soil. The two different ion exchange resins are shown on the right. Our next method is pumping, where water is pumped into the soil for the reservoir wells and flushes out contaminants. The last method is electroplating, where contaminants collect onto the electrode surface. Lastly, we will discuss how the electrolytic solutions work, specifically how the most popular solution, EDTA, works. EDTA is a type of chelating agent, and as such, it chelates, which is another word for attaching, to heavy metals and turns them into a form that moves around more freely and is more soluble than the heavy metal is by itself. This process is illustrated in the picture on the right. The heavy metal's new form or complex can then be easily leached or removed using another method out of the soil.
So one of the main influencing factors is soil type, and in general, fine-grained soils are more suitable for this process than coarse-grained soils, and that's for a number of reasons. First off, fine-grained soils have a high surface charge density. Clays actually carry a net negative charge, and clays are a very fine soil grain. So you need that charge in order to create a conductive environment for the actual process to take place. Fine-grained soils are also less permeable than coarse-grained soils, and that increases the need for electrolytic remediation versus conventional methods because when the soil grains are less permeable, there's less pore space in between the grains, and means that there's less space for these conventional methods to sort of occur, whereas you need to get like a little bit more creative with like the electrolytic remediation. Fine-grained soils also have a larger cation exchange capacity, and all that means it makes the movement of the contaminants with the electric field smoother. Like the contaminants will move faster within the porous medium. They'll move in like a more predictable pattern. And lastly, fine soils have a better water retention. And because they have a better water retention, that means they have more water saturation, which creates a more conductive environment because the water is needed, like the ion movement in the water is needed to make the process happen. So if you don't have the water there, you don't have electrolytic remediation. And then here's just a little refresher about fine versus coarse soils. Like as you can see here, there's just more space in between the coarse soils that gives the space like the conventional methods room to operate versus how it's more compact. Like water is going to flow through less easily, which makes it more difficult to use conventional methods. And then here's the table with all the different permeabilities. And as you can see, clay, which is our negatively charged soil, has the smallest permeability on this list. Another influencing factor for our process is contaminant type. The most effective for remediation, the most effective is heavy metals, radionuclides, and charged organic compounds. And this is because all three of these contaminants exist as charged species in water, and that makes them easy to extract with electrodes. In the case of metals and radionuclides, they're positively charged, which means they're going to bond to the negatively charged clay particles via the cation exchange. And as I mentioned earlier, the cation exchange makes the movement through the porous medium more smooth, so it means it's going to flow easier towards the cathode. As far as the charged organic compounds go, you can use surfactants, such as Elizabeth mentioned with the EDTA. And then the EDTA can attach to the charged organic compounds and make them more responsive to the electrodes. One contaminant type that's not as typically used when it comes to electrolytic remediation is denapel, and this is because denapel is immiscible with water molecules, which means it doesn't mix, which means like the electrokinetic remediation depends on the ion movement in the water. So as you can see with this little visual here, the denapel exists in a free phase, like a completely separate phase from the water, which means it's not going to react to the cathodes or the anodes. Also, due to the high densities, the denapel is going to sink deep in the subsurface, which makes denapel treatment with an in situ process, such as like electrokinetic remediation, more difficult. And on top of all this, denapel is not typically charged. And if the denapel is not charged and it's content in its current state, it's not going to react, or it's not going to want to lose or gain charge, which means it's not going to react to the cathode and the electrode. The electrical gradient is another influencing factor, and it's actually what makes this process possible. So the electrical gradient develops due to the presence of the cathode and the anode. And if the electrical gradient develops countercurrent to the hydraulic gradient, then the reverse flows occur due to advection. And that's important because that means that you could use this method regardless of the hydraulic gradient. So if you want to pump water against the hydraulic gradient, with conventional methods, that's not really possible because the conventional methods rely more on the hydraulic gradient. But with this method, you can use the electrical gradient and pump the water towards, or pump the contaminant towards the cathode or the anode. So for example, if you're pumping like a heavy metal, if you want to go against the electrical gradient, you would put the cathode up here and the anode down here, and the electrical gradient would flow towards the cathode, and the water flow would flow with the electrical gradient as opposed to flowing with the hydraulic gradient. The last influencing factor I want to talk about is pH control. Reactions at electrodes create a pH gradient, and it changes depending on which electrode you're at. For the anode, if you're at the anode, it's going to lower the pH. It's going to create an acidic condition, allow for the easy dissolution of the contaminant. And that's going to improve its mobility in the water. Again, it's going to make it easier for the contaminant to flow in the porous medium, to flow to the electrodes. At the cathode, it's going to raise the pH, and that's going to create alkaline conditions and allow for the controlled precipitation and allow for the controlled precipitation for the collection of the contaminant. So the cathode's going to cause if you're working with like a heavy metal, it's going to cause the contaminant to precipitate, and then you could pump that out of the water and treat it. So the two oxidation reduction reactions we have here at the cathode, reduction is going to occur, which is going to release the OH minus and increase the pH. As you can see here, you're gaining electrons, so you're creating a alkalinic environment. Whereas at the anode, it's like the opposite. The oxidation occurs, and it's going to release H plus and lower pH. So as you can see, there's electrons in the product, which means it's getting more acidic. And then pH control is a good thing and a bad thing. The good part with pH control is it allows for selective removal because different metals are soluble at different pHs. So you can adjust the cathodes and the anodes accordingly to remove the metal you want to remove. But the downside to this is when you create a pH gradient, you're going to cause severe environmental damage in soils because the pH gradient is going to change the nutrient levels and the composition. It's going to affect the microbial life, and it's going to make normally neutral metals become toxic. And like when you adjust small things in the soil, these changes will have big effects on like the composure of the soil, and that's going to affect anything that relies on the soil for life.
Before we start our electrolytic process, proper site preparation is critical. First, we conduct geophysical services to map the subsurface. This helps us identify areas with low conductivity like clay layers and locate contaminant hotspots. Next, we check underground conditions. Our underground water must fully saturate the treatment zone because electrolytic process rely on water as a conductor. If the groundwater is salty, we need to avoid electrolytic process here to prevent any chlorine gas formation. Um, Finally, we mark utilities like pipes or cables to avoid drilling into them and planning access routes for equipment. The steps sets our stage for a safe and effective cleanup. And then we move on to electro network design. Designing the electro network is like planning a grid for electricity to flow through the soil. So our electrodes are typically spaced 15 to 25 feet apart, but in clay soil we place them closer to around 10 feet to boost the electric field. For contamination under buildings, horizontal electrodes are ideal, while vertical electrodes work best for deeper plumes, which we face in more general cases. Powering the systems would require a balancing voltage and current. We use 12 to 200 volts depending on soil resistance. Clay needs high voltage compared to sand. Our current needs to be kept very low to around 0.5 to 5 amps per electrode to minimize gas bubbles that would disrupt the process. For energy, we use grid power or solar panels with batteries, which are great for remote sites. To save energy, we can use pulsed DC instead of continuous current to reduce pH swings and save our energy. Monitoring would ensure that everything runs smoothly. We track voltage and current to confirm that the electric field is active. We track the pH and oxidation reduction potential near the electrodes to, to alert us to acid buildups around the anode or the cathode to notice any imbalance that can stall our process. We also test groundwater for contaminants and byproducts. Some of the tools we can use are inline sensors, for example, pH or oxidation reduction potential probes. Um, we can also use voltmeters to track the voltage and current at the site. We can also use remote sensors that sends real-time data to laptops so we can adjust voltage automatically if pH have a dramatic change. We can still face some challenges during our process, so we'll provide some mitigation to fix them. First, if our pH is imbalanced, that will be acid at the anode or alkaline cathodes that can harm our microbes or clog the soil. We will fix that by injecting buffers at the anode or the cathode to re-establish balance of pH, or we can reverse the polarities. Next, we can also face gas buildup during the process, which will be hydrogen, oxygen, and chlorine gas at the cathode and anode. That will require us to include venting systems in our process, and also avoiding salty groundwater would avoid chlorine gas from forming. Lastly, we have electrode fouling, which would be minerals like calcium carbonates that can coat our electrodes and block our current. We can then clean them with acid washing, mechanical cleaning, or replace our sacrificial electrodes.
Items are used in the field. The devices used in the field are a DC power source outside of the area being remediated, a negatively charged cathode, positively charged anode, 2 reservoir wells, 1 for each electrode, a drill to place tubes or rods, and an injecting device for the electrolytic solution. Now let's look at some of the electrodes that can be used. There are many different materials that can be used to make electrodes for electrolytic remediation, but whatever is used must not react with the electrolytic solution or the ions around it during the process. Essentially, the electrodes must be inert. The electrodes can also vary in size depending on what they are needed to remediate. Some of these sizes for carbon electrodes are shown off to the right of the slide. The 3 most used materials for electrodes are carbon, graphite, and platinum. We now move on to drilling methods used for electrolytic remediation processes. The preferred method for this type of work is usually direct push injection or DPI. DPI uses a drill located on a vehicle or machine. This drill either utilizes pneumatics or hydraulics to push both a rod and a drill string into the soil. DPI is used both to place tubes or rods that the electrolytic solution will travel to reach the wells and to inject the electrolytic solution itself. This method is usually best if used on unconsolidated soils like sand, gravel, clay, and silt. I'll be discussing electrolytic solutions again. The 3 most popular choices are EDTA, which we explained how it works at the start of the presentation, fulvic acid, and citric acid. All of these types of agents are extremely good at removing heavy metals from soil and other unwanted places. For example, EDTA is also commonly used as a medicine for people with heavy metal poisoning.
before we can talk about anything, we need to talk about Dr. Leo Casagrande. So he discovered that the coefficient of electroosmotic activity for most soils is constant in the range of 5 times 10 to negative 5 centimeters per second for a gradient of 1 volt per centimeter. And that value is significant because it's larger than the hydraulic conductivities of fine-grained soils, which makes electroosmosis actually more effective than conventional methods when it comes to removing water from soil. Another two more reasons he cites why electroosmosis is a preferred method for dewatering soil is because pore size and hydraulic gradient are independent of electroosmosis, and that's significant because a lot of times when you're dewatering soil on a construction site, you're going to want to work opposite of the hydraulic gradient, and because this method is independent of the hydraulic gradient, you can pump water in a way you wouldn't normally be able to. And then normally fine-grained soils have small pore sizes, which makes conventional methods less efficient, but because electroosmosis is independent of pore size, you can ignore that issue. So the first ever application of electroosmosis in the field was just dewatering for bridge construction. This occurred throughout the 1930s. And when I say dewatering, all I mean is just remove water from soil. So how this process works is that anodes and cathodes, and in this case cathodes act as the dewatering device, are installed in the ground, and positive charges are going to move the water from from anode to cathode. Water is then deposited at the cathode, and it's pumped and removed from the soil, and the soil becomes dewatered, which makes it more stable and more suitable for construction. And it makes it more stable for construction because you're not going to have the force of the water within the soil that could potentially knock the foundation around. And as you can see in this picture, the blue pipes are cathodes, and it's removing the water from the structure. And then a detailed diagram of what's actually happening here is, as you can see, the positive particles are moving one way, the water is moving the same direction as the positive particles towards the cathode, whereas the negative particles are moving towards the anode, and when it gets to the water, it's going to get pumped out. Or when it gets to the cathode, it's going to get pumped out, I apologize. And then when it comes to the scope of contaminant hydrology, an example of electrolytic remediation being used in the field is with the United Chrome Products Inc. Superfund site in Corvallis, Oregon. So a bit of a background on the site. So this company operated a chrome plating facility for about 40 years near an airport in Corvallis, Oregon. The production of chrome plates produces hazardous plating solution, and what the company would do with this solution is they dispose of it into dry wells and neutralize them with soda ash prior to disposal. And then for just a little bit of context there, a dry well is just an underground structure that's designed to collect the unwanted wastewater, and the soda ash is going to react with the hydrogen ions present in the solution to form water and carbon dioxide, which can decrease its acidity and make it safer to dispose of. And here's just a little diagram of the dry well. As you can see, you put the soda ash in there, you put the solution in there, and it's going to neutralize it. But what happened was indoor plating tanks at the facility began to leak the solutions directly into the soil and the groundwater, and that caused this site to gain Superfund status in 1984. The EPA had to move urgently because two city wells are located just 3,000 feet away from the site, so they couldn't risk the pollutants seeping into the drinking water of Corvallis. So what the EPA initially did is they excavated the contaminated soil in 1985. As you can kind of see here, how the whole ground is kind of leveled, that all used to be soil that the EPA removed. But even despite isolating the area and removing a bulk of the soil, there's still contamination remained in the site, so they need to find a way to remove that. And then here's just a bit of a site timeline for more context. As you can see, site inspection occurred in 1983, and then a preliminary assessment occurred in 1984. They saw how contaminated the area was, and then from there, they've just been applying a bunch of efforts to remove as much solution as possible. So the main contaminant that the EPA was worried about in this situation was hexavalent chromium, and that was the contaminant that's being leaked from the plating solution. Hexavalent chromium is extremely acidic. It carries a +6 valence state, and it's also toxic. It's a known carcinogen in its hexavalent form, and this carcinogen targets lungs, kidneys, liver, eyes, and skin. So obviously very bad, but this site was suitable for electrolytic remediation because hexavalent chromium is a heavy metal, which, as we learned, is the primary contaminant you want to use when you're using, or you want to remove when you're using electrolytic remediation. And Western Oregon soils are generally high in clay content, which, as we know, clay carries a negative charge, and clay has a low permeability, which makes it more suitable for electrolytic remediation. So what the EPA did, or what the city did, was they used in situ reduction and precipitation. So in situ reduction, which is just ISCR for short, is a type of electrolytic remediation process. And how that works is you pump the reducing agent into the groundwater, and that can be done through a direct push injection, which, as you can see, that's what's being done here. They have drills, they're pushing the agent down to the soil, or you could use on-site wells. And the idea is you want to get the reducing agent circulating as much in the soil as possible in order for the process to be effective. If you want to see how it's done with like wells, as you can see, these are pictures from the Corvallis site. And as you can see, there's monitoring wells and there's an extraction well. And what you do is you'd pump the reducing agent down one well, and then you'd extract it from the other well. And that would create a flow of the reducing agent in the ground in order to spread it as much as possible. So the way in situ reduction works is you're going to take a reduction agent, typically that's zero valent iron. And what zero valent iron is, it's iron with no charge that readily wants to gain a positive charge. So it's going to be eager to release electrons, and the hexavalent chromium is going to want to accept those electrons to become chromium 3+. And chromium 3+ is perfect because it's a common nutrient that is perfectly safe. You don't have to worry about toxicity or any of that. So here's the full redox reaction. We have Cr2O7 2- plus the zero valent iron plus the H+ ions is going to turn into Cr3+ plus iron 2+, which is normal, and just water as a byproduct. And all Cr2O7 2- is a dichromate ion, which is a common form of Cr6, which is a common form of hexavalent chromium. And what's unique or cool about this reaction is you don't need a cathode or an anode, because you're using the flow of the reduction agent. And here's just a bit of a further breakdown of the redox reaction. So it's a really simple process. The hexavalent, or not the hexavalent, I apologize. The zero valent iron is going to release electrons, and the hexavalent chromium is going to accept the electrons. And since zero valent iron donates 2 electrons, you're going to need 3 zero valent iron atoms to produce 2 hexavalent chromium ions. But even after that, you still need another step, because you don't want oxidation occurring. And what that means is you don't want the Cr3+ returning to its Cr6+ state. So what they do next is they use precipitation reactions. So this turns the 3+ chromium ions from the aqueous phase to the solid phase, which immobilizes them. And then from there, they're pumped out, and they use filtration processes to remove the chromium. So these filtration processes can be like coagulation and flocculation, or filters like gravity filters or pressure filters. And then it's beyond the scope of the presentation, but if you need a reminder of how coagulation and flocculation works, there's a little diagram for that. So how the precipitation reaction works, I use soda ash as the precipitating agent because that's what the site used initially. But you're going to want to use this react soda ash with the water, and it's going to form carbonate and hydroxide. And then the hydroxide is going to react with the chromium 3+ to form solid chromium. And then from there, the precipitate gets filtered out. And then the site progress since then, the site condition is still improving. It's not off the national priority list yet, so it is still classified as a Superfund site, but is improving significantly. The concentration of chromium was initially 1,000 parts per million, now it's just 35, and it has its next EPA designated site assessment in 2027.
So we'll start with applicability. The first thing I wanted to cover under that would be target contaminants. There are kind of 2 factors that influence whether or not this remediation method will be applicable to a site, the first of which being target contaminant. So heavy metals are like the most typical contaminant that this type of remediation will be implemented for. Unlike organic contaminants, heavy metals can't be biologically or chemically degraded, so they can easily accumulate in soil for long time periods, which is a problem. So specifically for this type of remediation, metal compounds respond very well to the electric field that's generated. And so that field is able to influence the migration of the contaminants using that electric potential. So additionally, heavy metals are water soluble, so they'll dissolve in the groundwater and then be able to travel to the anode or the cathode depending on their charge with the water flow. Another type of compound or contaminant that is typically used, or this type of remediation is typically used to target, is organic compounds. Polar compounds work very well for this type because they have surface charges that respond to the electric field. So you're able to use an electric field to kind of influence the behavior of those compounds and get them to travel with the water. One slight issue you can have with organic compounds is if they are not water soluble, but luckily you're able to add solvents or surfactants if you need to make those compounds more water soluble. Additionally, some organic compounds will actually degrade under the conditions that are induced in electrolytic remediation. So at that point, you don't even have to worry about removing them from the anode or the cathode. They'll just degrade under the electrolytic state. And then some examples of compounds that would fall under the category of organic contaminants would be VOCs, SVOCs, which are semi-volatile organic compounds, and petroleum hydrocarbons, phenols, and etc. A final type of compound that can be removed from soils with this type of method is radionuclides. Radionuclides are unstable forms of chemical elements. They release radiation as they break down and try to reach a more stable state. These work under this type of remediation because they typically carry a charge. They're not as effective, or remediation isn't as effective in removing radionuclides as it is heavy metals, but it still does work a little bit because they are charged. And then some of those compounds that would be removed that way would be strontium and cesium. The other part of the environment that influences whether or not that electrolytic remediation will be applicable is the properties of the media, so like the soil type. Electrolytic remediation has been implemented successfully in materials including soil, sediment. It's used in groundwater. It's also been used in wastewater sludge before, and other porous material. The most important soil property typically for this type of method is the saturation of the soil. It's preferred for use in saturated soils, although it can be used in soils that would be considered unsaturated. I believe you need at least a 10% water content in your soil to be able to use this type of remediation method. The saturation of the soil is important for this type of remediation because you need to have the contaminants dissolve into the groundwater to migrate. So if you don't have sufficient groundwater contained in the soil, the contaminants won't be able to dissolve and be transported with that groundwater flow. Additionally, it's preferred for use in low permeability because it doesn't rely on the hydraulic gradient. You can use electrolytic remediation for a wide range of permeabilities, but it's most typically seen being used in low permeabilities since other remediation methods aren't as effective. So clays and silts would be your most typical candidates for electrolytic methods. Something that goes in hand with that is like the typical negative surface charge that you find on clays, which Billy explained a little bit previously. Additionally, you would want a low hydraulic conductivity. This typically just corresponds with a low permeability, so that's another factor you would want to keep in mind. And then there are a couple of other factors that influence the applicability of electrolytic remediation, but they aren't as important as the contaminant type and media type. So the pH of the soil, the initial pH of the site isn't very important, but the way that pH becomes an issue with this type of remediation is the pH gradient that's created over the course of the remediation. And then the organic content and contaminant concentration aren't very crucial either. This type of remediation tends to work very well for a wide range of contaminant concentrations and is quite effective. So that's not as important as the media type or the contaminant type. And then I also threw on in situ versus ex situ in here. In situ would be a lot more cost effective, but if you have like a highly contaminated soil or you're looking to produce a higher quality end result with like a higher removal rate of contaminants, then you might want to investigate ex situ methods. All right, so a couple of limitations. The contaminants must be water soluble. If the contaminants aren't able to dissolve into the water, then there's no transport mechanism for them. So that's probably the biggest limitation on this type of remediation. Luckily, if you do have components that aren't water soluble, you can typically add reagents or surfactants to the water that will actually encourage the dissolution of those compounds into water. So you can kind of get around that first limitation a little bit, just depending on what the type of contaminant is. Another big limitation comes with the tail end of this remediation process. A large pH disruption does occur to the site over the course of this remediation, since you have the water molecules splitting at the anode and cathode, so you'll end up with a very highly acidic end and then a lower, or you'll have a basic and an acidic end of the pH spectrum that you're creating within the soil. So that's an environmental impact that you have to keep in mind. So if you're conducting this at a site where the soil or just the environment wouldn't be able to tolerate that kind of pH disruption, then that would be something to keep in mind, and you would probably want to select a different type of remediation. Another limitation deals with just the speed of remediation. So if you have unideal soil properties, then it's going to take a longer amount of time to get that contamination out. So that would probably be a reason that would discourage you from choosing this remediation method. Another limitation is electrolytic remediation typically targets a large range of contaminants. So you may unintentionally end up targeting a contaminant that you weren't trying to remove. So it's very important that you understand the composition of all of the compounds and contaminants in the groundwater that may respond to the electric field that you generate as a part of this process. So that's another limitation to keep in mind when you're choosing your remediation strategy. And then finally, if you have buried metal objects, those can interfere with the electric field that's produced through this method. So if you have a site that had buried tanks or storage containers that are leaking underground, but the actual metal structure that had the spill is still remaining in the ground, this is probably not a remediation technique you'd want to choose, because that large metal object can interfere with the way that the electric gradient works, which is not something that you would want to deal with. All right, next I'm going to talk about the cost and availability of electrolytic remediation. So I broke it up into the difference in situ methods and ex situ methods. So we covered pretty much exclusively in situ methods for this presentation, so that's going to be the more significant chunk of what I talk about here. When you treat soil in situ, that means that the soil stays on site exclusively. There's no moving soil around to take it somewhere else to treat it. And the cost for an in situ treatment is going to vary significantly based on the nature of the site and then a bunch of factors just pertaining to the site. So you have to take into account the area that you need to treat. That kind of deals with how many electrodes are you going to need to install. If you have a much larger area of contamination, you're going to need more electrodes, which is going to cost more money. This also goes hand in hand with the depth of contamination. So if you have contamination that reaches to a greater depth in your soil, that's something that will need to be taken into account in the electrode design. So you'll need to dig deeper wells, and you'll need to install electrodes deeper into the ground. So obviously that would be another another point that raises your cost. The soil properties influence the price because soil properties that aren't ideal for this type of remediation are going to extend the duration of time that it takes to remediate a soil. And obviously, time is money. If you're paying a certain amount for electricity and you're paying that over a longer time frame, then you're going to end up paying more money versus if you could select a different remediation method that would get this process done quicker. The contaminant properties also play into the cost. So you have to look at what the concentration gradient of your pollutants looks like. Do you have like a very high concentration plume like in one place and you can kind of keep it contained and remove it there, or is it a smaller concentration but spread out over a greater area? That's another factor on how many electrodes you're going to need and where you're going to install them. And then a final price point is just the cost of energy and your access to energy. If you're going to choose to use energy from like a local grid for this, your price is dependent on, you're pretty much at the mercy of that electric company for how much they want to charge you for electricity. You also have to consider your distance from the nearest electricity generation place. If you are very far away, then you might want to look into an alternative energy source such as solar, but again, just your access to energy and like the local electricity costs is going to be another major factor that determines the cost. So the way that the price is distributed over the lifetime of a site kind of starts with the largest investment happens up front, because you have to investigate the site and then construct the site prior to even beginning the project, essentially. So before you start the project, you need to know what your soil and contaminant properties are. So you'll need to do some surveying, take some samples, and figure out what area you need to treat, like what contaminants you're treating for, what the extent of contamination is. Once you have all of that information, you can design your system. So that would be how many cathodes or anodes do you need, how big, where do you want to place them. From that point, you could go on to start the actual construction of your site, which is probably the most expensive part of this whole process, since that's where you need to either construct or purchase the electrodes. You need to install them. If you need surface facilities, that would be another thing that you would need to construct. If your site is remote, you would need roads to get your equipment there. So constructing and setting up the site is the largest investment that you're going to make for a remediation like this. And then once the site is up and running, you have your electricity costs and you have the cost for any like chemical additives that you would need. So on a daily basis, you'll be paying for the electricity to run your electric field that you're generating, and then you'll need the electrolytic solution around the cathodes and anodes. If your contaminant isn't the most water soluble and you need to add a surfactant to get that to dissolve into the water, you'll have to pay for the chemical expenses for treating that. And then additionally, throughout the course of the remediation, you'll need to do routine monitoring just to ensure that the remediation is effective and that everything's going to plan. So you'll need some monitoring wells, you'll need to take samples periodically, and stuff like that. And then finally at the end, you also do have a slight remediation cost with this type of remediation, which is unfortunate that you have to remediate after the remediation, but this just ties into the pH gradient that can be created in the soil as a result of this process. So this typically involves digging up the soil like directly at the cathodes and anodes, since that's where you have the largest pH disruption. Sometimes you can have like loss of vegetation in the area as a result of that pH gradient, so that's just another factor that you need to address as your final closeout of the remediation plan. So I've included a little graph on this slide that kind of ties in the main factors that deal with your like daily operating cost. This was a study conducted, so it's across 4 experiments that deal with different levels of contamination and slightly different approaches to using electrolytic remediation. And through these experiments, this lab was able to estimate your typical cost for this type of remediation. So that comes out to about $110 to $508 per cubic meter. If you want to use enhancers to further enhance the effectiveness of your treatment or increase the amount of contaminants you're removing from the soil, then that price can jump up even up to $1,000 per cubic meter. So that's just another trade-off of how much do you want to spend versus how much contamination do you want to remove. Okay. And then on the other hand, you have ex situ methods. I won't cover this as much or nearly as in detail, but this is where you're taking the soil to an off-site location for treatment. The cost is based on many similar factors to in situ, and then it has a couple of its own ones. So area and depth of contamination and concentration of contaminants in soil properties, those are all very, very similar to your factors for in situ, so I'm not going to cover those. But your biggest additional costs with ex situ come from the transportation. So moving dirt is expensive. You don't want to have to move it any further than you need to, so you have to take into account where is the site that you're going to be treating this dirt, how far is it from the actual remediation site, and then ex situ tends to be more disruptive to the environment, so your remediation is kind of a little more intensive since you have to bring all the dirt back and get the site back to the same condition it is before you excavate it. So additionally, it can be more expensive than in situ, but typically produces a more thorough treatment. So there are pros and cons to both. That's just something you have to consider when you're choosing a method. All right, and then the last thing that I wanted to cover is the availability of electrolytic remediation. So it is available for commercial use, and it is currently in use at a field scale. There's no one firm that kind of has complete ownership of like the concept, but there is a company called Geokinetics International Incorporation that developed an electrolytic remediation technique along with Lockheed Martin that's currently in use in Europe. So they have that technology patented in Europe, and they have like multiple sites where it's in use and it's successful there. And then in the United States, Tehran Corporation prides themselves on being the leader in large-scale electrolytic process installations. They have a patent called lasagna, which is called that because it's a series of planar electrodes. So it kind of looks like lasagna, but like vertically. So that's in use in sites all over the United States right now. It's very cost effective. They estimate it's only $75 per ton of soil treated, which is very competitive compared to the prices that I discussed on the last slide. And they do currently have like a contact if you have a site that you would like to implement this technology to. They will, if you call them, they'll install it for you. So that does make it very available in the United States. All right, so I believe that's all we wanted to cover for today. Thank you.